This is video lecture for week 8. In this, we continue application of differentiation. Here we discuss maximum and minimum values, absolute maximum and minimum, local maximum and minimum. Let's start with absolute maximum and minimum. For a function f defined on the set S, means let's first understand this too. F is a function, and for every function we can draw a graph. So this is the graph of f, this is the graph of f. And what is this set S? This is the domain of the function f, where f is defined. That means this function is defined for the values of x from this point to this point. You see this point, the function graph is defined from here and till here. So this from here to here, it is a capital S. And for similarly for this graph, so this is the start of S and this is the end of S. So this is capital S. So we take any C between from S, that is between in this interval. Then the value of that C, that is Fc, becomes an absolute maximum if Fc is greater than Fx for all x in X. That means this is your graph and this is S and this C is in the S. Am I right? So here the value of C is here, that is Fc, and look at this Fc. This Fc is greater than all the values before and all the values after. That means all the values from here before C and after C, from this, if you find the value of Fx, they are all lesser than this Fc. Then this Fc becomes absolute maximum. Similarly, if Fc is less than Fx for all x belongs to S, then it becomes absolute minimum. You see this one. Same, this we have S, C from S, then I find the value of C, that is Fc, this value. You see this Fc is lowest, say minimum, which is lesser than what you call all this one. So that means all the values from here to here are greater than Fc and all the values after this are all greater than Fc. Therefore, this Fc becomes an absolute minimum. So the question is here whether every function has an absolute maximum and absolute minimum. The answer is no. You see, in this one you have absolute maximum, there is no absolute minimum. In this example, we have absolute minimum, but there is no absolute maximum. But before I move on to the next, you have to be little careful about the words, or you can say the singular and plural terms of these what you call maxima, minimum and absolute, etc. So check here, maximum is a singular, maxima is plural for that, minimum is singular, minima is plural, absolute maximum or absolute minimum is also called absolute extremum. Any one of this, right? Any one of this is called absolute extremum. If you combine them, it becomes extrema. So extrema is plural of extremum. Okay, so remember these words which we will be using quite frequently in this what you call week 8, in this particular topic. So let's see some example here. This is very interesting example because we are going to draw the graph. We will see what are, we will find the absolute extrema of this function in 3 different S, that is 1 minus infinity to infinity, this is capital S, another minus 3 to 3 open interval and minus 3 to 3 closed interval. So for three different s, we see what happens, what are the low absolute extrema of this function. So what we do here is that we just substitute x is equal to 0, and I just substitute these 0 and I get minus 9 here. Now just check here, all the values before this you substitute in the function fx. They are all what you call greater than minus 9. All the values you substitute after what you call 0, you will see that they are all greater than f0, that is minus 9. So therefore f0 is equal to minus 9 in an absolute minimum. And here the s is minus infinity to infinity, that the entire domain here. And you see the graph here, the graph is goes on opening. That means as I increase here this side and this side, and that means I will extend this what you call, since the s is minus infinity to infinity, if I goes on take the values greater than 3 and less than minus 3, what happens? This graph is goes on opening. That means here is for this graph in this interval, okay, there is only absolute minimum, there is no absolute maximum. Now we change this s to open interval minus 3 to 3. The same graph I will draw here. You see, since it is open interval, I put the open circle here. So this is the graph of this. Again, this is the absolute minimum, and this cannot be absolute maximum. These two cannot be absolute maximum. The reason is here, they are open interval. So for this graph, for this what you call interval, we have absolute minimum, but there are no absolute maximum. Same for this. Although I reduce the what you call interval in this way, but because of open interval, there are no absolute maximum here. If I take the closed interval, you see this, so I fill this circle, no open circle here. Then what happens? You have absolute minimum as usual, but there are two absolute maximums here. You see, here and here. There are two absolute maximums. So for the same function, if I goes on changing the s, so three different conclusions we draw here. So let's say now local maximum and local minimum. The difference between absolute and local is that in the absolute maximum and absolute minimum, we take the entire domain of the function. In the local maximum and local minimum, we take part of the domain. The definition of absolute maximum, absolute minimum and local maximum and local minimum is the same, that is this part. The only thing is that here I change for all x in some open interval, that is this open interval of the domain, that is yes, that is capital S. Let's see this graph now. Suppose if I draw the graph of this, this is the graph of f. Now what is your s here? S is, see, s is starting from here and s is ending here. From here to here we have capital S. But here I am not taking the capital S, I am taking open interval, some open interval containing C. So for example, let's see first this example now, definition. Fc is local maximum, same condition for all x in some open interval. What is this open interval for this question? You see this example. This is, you take part of this what you call graph, not the entire graph. You take only this part of the graph. When you take this part of the graph, what is your open interval? Open interval is from here to here, is the open interval. And this is your Fc, and this is local maximum. This is local maximum for this open interval. But is it the maximum For the entire graph? No, because for this part of the graph, this is the maximum, but for the entire part of the graph, this is the maximum. So this is absolute maximum, this is local maximum. So that is what the difference. So similarly, local minimum, some open interval. What is this open interval? You see, for this to this is the open interval for local minimum. So this is the local minimum for this part of the graph. But is it the local minimum for the entire part of the graph? No. This is the absolute minimum for the entire part of the graph. This is absolute minimum. This is the local minimum. Now look at it. For this part of the graph, from here to here, this is the local maximum. And it is also absolute maximum because it is the maximum of all. This is the local minimum for this part to this part, and it is also absolute minimum for the entire graph. So careful that local is for part of the domain and absolute is for the entire domain. So you see, this is the graph of that. But one interesting thing we can find here is that whenever you draw the graph and wherever the local maximum or local minimum happening, two important things is happening. One, the local extremum seems to occur either at a point where the tangent line is horizontal. You see, at this point you draw the tangent, it is horizontal. At this point you draw the what you call tangent, it is horizontal. Whenever the tangent line is horizontal, f prime x equal to 0. So you see, f prime x equal to 0 here. Here also f prime x is equal to 0. Or you draw a line here, it is not a tangent, and you draw a line, it is not a tangent because this is the corner, or you can say sharp edge. Wherever you have a sharp edge, we know that the derivative is not defined. So that means at this point there is no tangent, that means derivative is not defined. At this point there is no tangent because the derivative is not defined, therefore the derivative is not defined. So our sharp edges, there is no derivative, but wherever you have a curve, there is a tangent. So here the derivative defined, derivative is defined, derivative is not defined, derivative is not defined. That means at this point 1, 2, 3, 4 you have local extremum, right? So local extremum happens only at two cases. Either the derivative has to be defined or the derivative has to be not defined. So we will see in the next video lecture the detail about that how to find this local maximum and local minimum. Thank you.